Swayam Prabha. Digital India. Educated India.
Okay, let's get back to this. So we'll continue with more, a couple of more things from advanced cryptography. Just to go back to this. What we are going to do is, secure multi-party computation and digital cache, and it will be at a very high level. We won't see, many protocols or anything except something in the context of secure multi-party computation. But I'll start with digital cache, just a couple of slides to give you a high-level idea. So it's not cryptocurrencies, it's not Bitcoin. This was actually proposed in the cryptography literature way back in 1983, before notions like zero knowledge were there, for instance. Or many of the definitions that we take for granted today, they were not there. But still it was a pretty interesting, solid idea. It got improved upon a lot since then. And the inventor of this, David Chaum, he actually made a company called DigiCash. And it was deployed by a few banks in Europe, something in the US. So in the Europe, I think Deutsche Bank was one of the bigger ones. And it ran for a few years, but unfortunately, it didn't take off. The company went bankrupt in 1998. People were just happy with using credit cards at that time, I guess. So it didn't, and there were some quirks about this particular thing I'm going to talk about in the next slide. Somehow all that together, it was not a business model that worked at that time. Could it work now? Possibly, but the company doesn't exist. There is some academic and commercial interest. People are still improving on this. There is an open source software that implements some form of DigiCache, but not at the same level that it was in the 90s when it started. But it's an interesting question. Could something like this be used or revived now? Right now that the banks are, the governments are doing. So CBDC stands for central bank digital currencies. Okay, so what is the model for digital cache, for this notion of digital cache? So it's mainly for doing transactions for, say, buying things. So there is a customer who wants to buy things from some merchant and pay cash for it. Of course, the cash comes from some bank. There's a bank involved. And the cash kind of goes back to the bank. The merchant will deposit their money back in the bank. So the bank is going to maintain accounts for all these people. Okay, and they withdraw cash from this account, they deposit it back into those accounts. And so the first thing that a customer would do is to withdraw some cash from this bank, right? Now, how does a digital cache look like in this case? The most obvious way would be you go to the bank, say, I want to withdraw this much cash, and the bank would give you some sort of a digital token. This is probably how something like e-rupee would work. But the problem with that is the bank knows which token they gave you, and they can later, when that token gets deposited back by a merchant, they know that you went and spent it with that merchant. And there is no anonymity, the kind of thing that you would expect from currency notes, right? So we are not going to have the customer just go up to the bank and say, give me cash. I mean, they will say, give me so much cash, but the bank is not going to give the customer some tokens that the bank can see what they are. Instead, they would use a cryptographic protocol. What kind of protocol? It's a magical protocol, and there's the same kind of magical protocols that we'll be talking about in the next part of this lecture. So you could think of them as secure computation protocol. But this will be something very special, very specific, involving some blind signature. So the tokens are going to be some sort of unforgeable tokens with a signature from the bank. The unforgeability comes from the fact that it's signed by the bank. On the other hand, the bank only learns your ID and the amount you're withdrawing so that they can deduct it from your account. They don't see the token number, anything so that can be linked to the token. So the bank doesn't know which token you got. The token number gets generated randomly in the protocol in a way that the bank doesn't know that token number. And nevertheless, the bank will be able to put a signature on that unknown message. So that's what's called a blind signature. It's like something you do in physical world also, right? You have a sheet of paper, you want to sign at the bottom of it without reading the content. You put say a carbon paper on top of it, and you sign on top of the carbon paper. So you don't know what you sign, but for some reason you're happy to sign it, right? So here also, the bank is happy to sign it. They know that they're signing a token for this much amount, or so many tokens, but they don't know what exactly is the content of that token. Okay? So they will, the customer will get these kind of signed tokens, unforgeable tokens, and if you look at that token, it doesn't reveal this ID. Because what we are going to do is that if the token had that ID in it, it defeats the purpose again, right? When that token eventually gets deposited back, the bank will know this merchant is depositing this token. I didn't know when I issued this token, but I see this person's ID on it, so I'll know what it is. So the ID is not there in the token. Okay? Well, it's kind of there, but in a hidden form, and we'll see why it needs to be there. All right, then another protocol in the whole scheme is that the customer can go and make some purchase and transfer some money, right, to the merchant. So this is there's a verifiable process. The merchant wants to make sure that you're not claiming that there's a token I got from the bank. So you are kind of giving a token. The merchant should be able to verify the signature on it. But it's also something that you're authorizing. You're giving an authorization to the merchant to say you can now deposit this. Okay, it's a you could think of it as there's a deposit authorization that you're giving to the merchant. And the merchant, when they get the token, they don't really know your ID, nothing. All they know is that okay, this is for so much amount. It came with an authorization verifiably from whoever owns this token, to whomever it was issued. And at the end of the day, the merchant has collected a bunch of tokens like this. They can go and deposit all of them to the bank. So they don't have to wait. It's not like as soon as they get the token, they have to contact the bank and make sure it's good before accepting it. They can do the verification locally, and that would reduce the load on the banks. That would make the whole transaction faster. You don't need to create a bottleneck at the bank with everybody trying to verify all the transactions that are happening all over the world, right? So this depositing token is done, at the end of the day, in the middle of the night, something like that, when things are less busy. Now, what are the requirements we want from this digital cash system? So one thing in this whole thing is about anonymity. You want to have, you don't want any sort of fake money or anything, but on top of that, you also want anonymity. So let me start with this anonymity part. Even if the bank and the merchant get together, they shouldn't be able to see a token that was given to the merchant. They shouldn't be able to see from whom it came. Okay. So clearly the merchant shouldn't see, but that's not just that. Even if the bank gets together with them, the bank who issued that token, they shouldn't be able to trace back when they see that deposited token. They shouldn't be able to trace it back to which issuing protocol this came from. Okay, so that's one unlinkability. In particular, they shouldn't learn the ID in the token. Okay, that's why the ID is hidden. But on the other hand, and this is very crucial for money, you don't want double spending. You don't want this customer to go and give this money to different merchants, the same token, right? Unlike physical bill, that's a problem with digital cash, right? You use it any number of times. You can keep a copy. You don't have to erase it the moment you spend it. So you can keep trying to double spend. And we want to catch, or we want to prevent a bank from a customer from being able to do that. We don't actually prevent it in Chom's scheme, but what we do is that actually it's not just Chom's schemes plus future, later revisions. You don't prevent it, but you will detect it. When you detect it, you'll actually find out who the customer is. Who is it that did the double spending? And so it's kind of magic. If you just spend it once, it keeps your ID hidden. You spend it twice, it reveals your ID. A lot like what we saw in the proof systems last time. You answer one challenge, it keeps information hidden. You answer two challenges, it reveals something, right? So this protocol here, where the deposit authorization is given, it's actually a protocol where there's a challenge. And if you have answered two challenges, with same merchant or two merchants, but on the same token, then the answer from the deposit authorizations, will have, you put both of them together, you can recover the ID of the person. Okay. So that's kind of preventing double spending, right? If you do that, your account will get they will, put a big penalty on you or something. So it's not in your interest to double spend. Of course, you can double spend, and for until the depositing happens, nobody will detect it. It's only when both of them go to the bank will the bank realize that double spending has happened. Another issue to take care of is maybe this customer was all honest. They only spent it once. The bank goes and says, look, this customer bought 2 items from my store. This is the first time they gave me the money. This is the second time they gave me the money. And you just show the same thing. So you're basically double depositing. But that won't work. This deposit authorization is something you cannot reuse. Okay, it's you cannot. You need to basically get the customer to do it twice to get 2 valid deposit tokens. Otherwise, it won't be. The bank will detect that you're trying to just deposit the same, copy the same thing, and deposit it twice. Okay, so that's pretty much the whole kind of set of guarantees. It's an old style security definition. There are a bunch of properties. It's not simulation-based security like zero-knowledge proofs that we saw, because this was before all that, much of this. Okay, but it's still a very reasonable security definition. The protocols are reasonable, but there is room for improvement. Any questions on this high level? I'm not going to go into the details of the protocol. Yeah.
Sir, but then how the regulator will know that the money is going from where to where?
Okay, here they don't. The whole point of digital cash is not to have traceability. So currently, when you withdraw cash from the bank, go and buy it in somewhere, the regulator is not able to track it. And the idea of anonymity here is that they shouldn't be able to track it. They should know things like, for purpose of tax, how much you earned, and so forth. But they have no business, the government has no business finding out what each person is doing with their money. Okay, so this is in that spirit. Okay, so now on to secure multi-party computation, which is a big field. What's the big idea? You have many parties who have data with them. They don't trust each other, but they would still like to pool their data together and compute on it. Okay. For instance, it could even be something like Google has all these web pages, indices. You have a search query. You want to ask Google to return some pages that match some query. And imagine you want your privacy against Google. You don't want Google to know what you're searching. Well, there is one solution, not a very good solution, which is that Google could send you their entire database. I mean, of course, impractical, but in principle, let's say, and you could search it locally. Then Google would have no idea what you're searching, right? But apart from the impracticality of this thing, that suggestion, there's another problem. Google doesn't want you to have all this data that they painfully collected, right? It's their proprietary data. So they want privacy. They're okay with answering your queries. They don't want to reveal all the data they collected. So both parties are in some sense mistrusting of each other. They're not okay with revealing their entire information to the other party, their entire input to the other party. Still, they would like to, it's in both their interests, to let this computation happen, to run this query on this database. They would both like to do that. So that's the setting we have. Mutually distrusting parties want to collaborate. Today, of course, you just trust Google, so there's no question of mutually distrusting. You just send your query to Google, and we are all kind of accustomed to being okay with that. But in a kind of more privacy oriented world, you wouldn't want to do that. Okay? So, more generally, not just this kind of query problem, in all these problems, you have this tension between utility and risk. So the utility that you would get if you could collaborate is that you could compute, you could get the outcome of, right? So the database is one input, the query is one input, the answer to the query is something they want to get, at least one party wants to get, and that's utility. It could be even more interesting than just a function computation. So that's an instance of function computation. Alice has x, Bob has y, and say Bob wants to learn f of x, y, right? But it could be more interesting in the sense that, for instance, Alice and Bob and maybe a bunch of others are playing a game. And they have various inputs, or maybe they're controlling a process, right? Say the power grid. There are multiple, suppose there are multiple companies feeding electricity into the power grid, and they would like to keep the power grid, under some in some stable state, for which they need to know a lot of parameters, readings of the voltage, current, and so forth. But this is proprietary business information. That will reveal things like how many customers I'm serving, how much money I'm making, and the companies don't want to share it with each other. On the other hand, it's in their interest to collaborate and keep the power grid in a stable situation. So, and this is a continuing process. You keep having to change your various inputs to keep the grid in a stable state. So it's a process that has to be controlled jointly, and as part of that, everybody is using their private information that they don't want to reveal to each other. Still, they would like to collaborate, right? So that's kind of the utility we are looking for. The risk, on the other hand, as I was saying, is that to collaborate, these companies don't want to reveal their private information to each other. So that's one issue. Another risk is, maybe somebody could manipulate the output. Everybody says what their inputs are. Maybe everybody sends it to one party. They will compute it, but maybe they'll tell you something wrong. Okay, so that's another risk if you are going to rely on one party to do the computation, for instance. Okay, have a few more examples, along this line. So imagine there are two parties. There is an airline and there is a government agency. And the government agency has so the airline has a list of passengers who have booked their flights, who bought their tickets or who are coming to buy their tickets. And the government agency has a no-fly list saying that these people should not be allowed to buy a ticket, or they should not be allowed to board a plane. And let's say the goal is that the airline should see when a customer comes that they're on the no-fly list, and they should not be allowed to buy a ticket, or they should not be allowed to board the flight. Well, how do you solve it? So it seems like there are two options. One is that the airline could send the passenger list to the government. But that's very intrusive. The government can use it for surveillance. You don't want to trust the government to only use it on people who are on the list. Government agencies are notorious for using data in all sorts of even illegal ways, right? So you don't want to trust the government to respect citizens' privacy. So you don't want to make it easy or tempting for the government to collect all these data about who is flying when and where. Okay? Of course, a lot of that might happen in practice today, but we're talking about what should happen. So you don't want the airline to just keep sending all the passenger lists to the government. Okay, but what's the other option? The other option would be the government could send the no-fly list to all the airlines. But that's something the governments wouldn't want to do, right? Because it's very sensitive information. You don't want all sorts of airlines to figure out this list of people. There could be some sensitive information. So they don't want to reveal that either. And we have kind of a deadlock. You have to either one of them has to sacrifice their privacy. Okay, that's what it would look like. So so the utility is that you want to prevent this person on the no-fly list from flying. The options come with their risk. Both these options come with their compromises. So there's a time when you wish, suppose you had a trustworthy third party, then you could have the best of both worlds, right? You could get the utility. So there's a there's a third party who would take inputs from both parties, a list, a passenger list and the no-fly list, check for an intersection between the two lists, and just tell reveal the intersection to the airline. The government doesn't even need to know that these people tried to fly, let's say. And at the end of it, they will do this. They can be trusted to do this correctly, and then they would erase all this data and vanish. Okay, if we had such a trusted party, that's what we could have used. Unfortunately, this unicorn doesn't exist. Okay, so what do we do? Well, we could try to find some trusted parties, some outside surveys who is audited, and there will be a bunch of laws. If they violate privacy or correctness, they will be liable. We could try to enforce it by auditing, and so forth. But that goes only so far, right? It's just pushing the trust onto somebody else. We could have done that already with the airline, send them the no-fly list and say, oh, nobody should be allowed to look at this. What we can instead do, instead of actually having trust on either of these parties or a trusted third party, we can run this, we can get the best of both worlds using cryptography. Okay? So this cryptographic magic would be that these two agencies or these two parties would just talk to each other. Would just talk to each other in a protocol here, and at the end of it, they will get the outcome. So the airline will learn the intersection of the two lists, and nobody else would learn anything else. The airline wouldn't learn anything else about the rest of the list with the government wouldn't learn anything about the list with the airline. Okay. So we are emulating the presence of this magical creature using a protocol. That's what secure two-party computation would be. Here's another example to motivate this. Now, a few more parties. This is auction, where you're doing an online auction, but you'd like to do it without an auctioneer. So usually what is an auctioneer doing? They will collect bids from all the people and figure out which is a winning bid and how much they should pay. There will be some rule as to, there are things like second prize auction. So the winner is whoever has the highest bid, and they should pay the second highest bid. Okay? That's called the second prize auction. So there will be some rule, and we are trusting the auctioneer to do two things. Firstly, to do this computation honestly, and secondly, to maintain privacy, secrecy, right? You don't want, Alice sends a bid. You don't want the auctioneer to go and tell Bob, hey, this is what Alice's bid is. Why don't you bid 1 rupee more? So we don't want that. Okay. So we are relying on the auctioneer. We would be usually relying on the auctioneer to keep the secrecy. They are the trusted party. Can we replace them and have a protocol so that nobody trusts each other, but they're guaranteed that the winner is correctly computed and correctly, and no information is revealed other than what needs to be revealed. Oops. Okay. Yeah, some animation bug. But these are all supposed to be computers which look like hospitals. Given what happened in Ames recently, maybe these computers don't look good in these hospitals. But here, suppose there are a bunch of hospitals who have their patient records, their sensitive information. But they would like to pool this information sometimes, right? If you want to do some research on, or detect an epidemic or a pandemic starting, you would want to pool these resources. Or if you want to detect, find patterns about, what kind of treatments work. Just each hospital with their own data doesn't see the big picture as you could see by pooling data from a lot of hospitals. Unfortunately, pooling this data is often, illegal, as in you're not allowed to do that for privacy reasons. Also, like, even if you trusted all the hospitals can't trust themselves to keep their data private, right? So if you're collecting all the data from, or even if your hospital is good, you're working with some hospital who has a bad system, you're collaborating with them, right? You're sending your data to them to do this data mining. They might leak your information. Even if they're not malicious, they might be compromised. So you don't want, that to happen. So again, this is a place where you would like to have a trusted outside party to whom everybody could send their data. They would do the computation, tell everybody only the result, and then vanish. And we would like to replace that with a cryptographic protocol. And my last example here is an interactive process, or what's called a reactive process sometimes. It's a setting of controlling a process situation. So here it's a game. You're playing, say, a game of cards online. Usually you would trust a website to do it. Like, they are dealing the cards to all the players. They make sure that everybody here is playing one of the cards that was dealt to them. But that's putting a lot of trust in that website to run. They don't, first of all, bias the way in which they deal cards. They don't let, say, two parties collude and exchange their cards in the background. Or, so all of that is supposed to be enforced by this trusted party. Could we avoid the need for that trust? Instead, the parties would just run a cryptographic protocol, and they would know that it's as if there was a trusted outside party dealing the cards. So there, it has to do a bunch of things, right? As I was saying, it has to randomly shuffle. It has to make sure the cards dealt are disjoint from each other. Same card is not dealt to two people. When you play a card, it was one of the cards that was dealt to you. And even if a bunch of people collude, they don't learn anything about cards dealt to another player other than what their own hands would reveal to them. Okay, so all of that, would be ensured by a cryptographic protocol. So, that's the kind of cryptographic magic we would like to do without a trusted party, just by parties, mutually distrusting parties talking to each other, emulate a trusted party. And with a trusted party, there are many tasks you would like to do, right? Distributed data mining, auctions, games, or something like voting, at least in a process where everybody is, available at the same time to interact with each other. You'd like them to interact with each other and create the result, create the effect of having a trusted party instead of actually having a trusted party. Okay, in today's world, you would actually have a trusted party or multiple trusted parties often. And you're just hoping and relying on the assumption that they can be trusted. And we would like to replace that. All right, so this is what secure multi-party computation does. Okay, to replace the trusted party with a protocol. So let me start with, concretely, let me give a few examples. So one very useful but very simple computational task is what's called oblivious transfer. Okay, so what's oblivious transfer? So there's a sender and a receiver, and the sender has two pieces of data. Okay, So let me just get a picture here. Yeah, so the sender is this guy on the left. And there are two pieces of data. So in this case, let's say there are two stock prices, and they can predict. They have their complicated machine learning algorithm or whatever that tries to predict the stock price the next day. And they do it for two companies, let's say, so two stocks. And they sell the service to people who are investing in stocks. But this customer comes along and says, I just need to get the prediction for one of these stocks. That's all I'm investing in. Okay, so the seller says, sure, I have company A, company B, which prediction do you want? And this investor says, oh, I can't tell you which one. That's, which company I'm interested in is my private information. So I want either company A's or company B's prediction from you. I'm going to pay only for one prediction. These predictions are expensive. So I'll pay only for one prediction, but I can't tell you which one I want. And the situation of, where you need a trusted third party, right? Somebody could come in and get both predictions from the seller, from this predictor, figure out which one. So if you're a trusted party, the two predictions for the company A and company B will be sent by this predicting guy, and the investor would tell this trusted party which one she is interested in and retrieve just that information, right? So both of them are relying on this trusted party to do their job. The sender is sending their very sensitive, expensive information to them, hoping that they'll only reveal one of them to the buyer. And she is, sending her very private information as to which stock she is interested in to this trusted party. So if we had a trusted party, that's what we would do. But we don't want to rely on a trusted party. So we'd like to have a protocol where Alice and Bob, or these two people, will talk to each other, and at the end of it, they will learn exactly, so she would learn exactly one of them, the one she is interested in, and he would learn nothing. He would learn which one, he wouldn't learn which one was picked up. So this is oblivious transfer. So some information is being transferred, but obliviously, in the sense that, well, actually there's a little bit hidden from both sides. The sender doesn't know which piece of information was picked up. The receiver doesn't know what the piece that was not picked up is, right? If you remove either constraint, you can trivially have sender send both things and or the receiver send her choice to the sender. But with both these constraints, that sender doesn't want to reveal both pieces of data, receiver doesn't want to reveal which piece she is interested in, then we have a kind of a cryptographic situation that needs to be solved. Okay, so this is my little notation for saying, okay, the two-party protocol, this is a functionality we are interested in. Input from first party is x0, x1. Input from the second party is a bit b, and the output is only to the second party, and that is x of b. Okay, that defines the functionality of oblivious transfer. What we would like to do is emulate the trusted party that's carrying out that functionality. So here is a protocol. Okay, and I say this is a protocol that's secure against a passive adversary. Okay, what's a passive adversary? So we briefly talked about honest verifier zero knowledge in the previous lecture, where a verifier who is curious to learn some secrets of the prover, we said if say Bob is following the protocol, he wouldn't learn anything more. Okay, so it's an honest verifier there, and it's zero knowledge against an honest verifier. So this kind of an honest behavior, it's called an honest but curious behavior, is it's also called a passive corruption. Okay, so one way to think of a passively corrupted party is that they are running the protocol as prescribed, but somebody is looking inside their head, looking inside their system, and seeing everything that's going on there. So an adversary can only read they cannot change the process going on in this computer, they can but see everything going on there. That's what a passively corrupted computer looks like. Okay, so I'll show you a protocol that's only secure against passive corruption. So you could ask, is it a realistic model? Well, to some extent it is, because sometimes the way a system would be set up is you're supposed to run certain software as it is. You will be audited. You might use some trusted processes which will make sure you're running the right program. So to some extent, passive behavior can be enforced, that you cannot change your protocol. You have to behave as it is. But more importantly, or equally importantly, I guess, these passive protocols that are secure against passive corruption is the first step towards building protocols that are secure against active corruption. Okay, so this is an important, both theoretically and practically important model of corruption. Okay, so here is my protocol that's secure against passive corruption for OT. For OT stands for oblivious transfer. And we need a cryptographic tool, and it will be a public key encryption scheme. Okay? It's a public key encryption scheme with a little extra property, and that I'll say what that extra property is in a second. Okay, so here is a protocol. So there's a sender with two pieces of input, x0, x1. The receiver has bit B, and after the protocol, she would like to retrieve x sub B. So to begin with, she will run the key generation algorithm for this public key encryption scheme. And that gives her a secret key and public key pair. I've called it SKB and PKB, okay? Because she's also going to run, so for now, think of B as 0. Then she got SK0, PK0 by running this key generation algorithm. But she's also going to have a PK1, okay, another public key. But that she's not going to generate using this key generation algorithm. Instead, she is just going to sample it directly. So consider, say, Elgamal encryption, and this public key was, secret key was a little y, and the public key was g to the y, which is a group element, a random group element. And what we are saying is that we need a way to directly go and pick a random group element without knowing its discrete log. Okay, so that of course depends on the kind of group you have and all that, but many public key encryption schemes have this property that the public key can be directly sampled as a random bit string, for instance, without knowing anything about the secret key. Okay, so that's the extra property I need, the special property I need beyond the standard public key encryption, CPA security. So that's a property. One can sample a public key without knowing the secret key. So it's as good as somebody else sampled a public key secret key pair and showed you only the public key. So then she sends these two public keys, PK0, PK1, to the sender. Okay, so when b equal to 1, it is PK1 for which she knows the secret key. When b equal to 0, for PK0, she knows the secret key. And for the other PK, she doesn't know the secret key. Okay, now you probably can see what's going on. The sender just uses these two public keys to encrypt x0 and x1 respectively. Okay, so x0 is encrypted using PK0, x1 is encrypted using PK1. You get two ciphertexts, C0, C1. You send it, and what should the receiver do? Well, whichever bit she is interested in, for that she has the secret key. So she can decrypt it and recover the message, right, XB. And the other ciphertext is something she has no idea what it contains, because it's as if somebody else gave you the public key by sampling the public key in this special way. She has no idea what the secret key is. The CPA security guarantee tells you that the message essentially is hidden from you. Okay. Of course, this is secure only against a passively corrupt receiver. What if she was actively corrupt? Then she would actually, there's nothing preventing her from knowing the secret keys for both of them, right? So that's the part where we are relying on passive security for the passive corruption only for the receiver. But how about the sender? Well, as far as the sender is concerned, it doesn't learn anything about the bit B because because this is just two public keys which are distributed the same way. Whether you sample it using the key generation algorithm or you sample it in this special way, the output, the distribution is the same. Okay, that's the special property we want. So the view of the sender is independent of the bit B. So even if the sender were computationally unbounded, it doesn't learn anything about the bit B. Actively corrupt also, it doesn't matter. Actually we don't really rely on the sender sending valid ciphertext. It could send whatever it wants. It's in some sense as good as sending valid ciphertext. Yeah, but you can just worry about passive corruption. And now I'd like to, so any questions on the protocol? Okay, so it's a very simple protocol, and works against passive corruption. Let's see how to use it. And I'm going to use it for 2PC stands for two-party computation, secure two-party computation. Okay, and secure multi-party computation is abbreviated as MPC. For some reason, the secure part is not part of the abbreviations, but it's supposed to be secure. So how do you get 2PC from oblivious transfer? So oblivious transfer itself was a 2PC, right? An instance of 2PC for a very specific functionality, the oblivious transfer functionality. But now I'd like to use it to do, to have a protocol, secure protocol for an arbitrary function evaluation. So Alice has X, Bob has Y, and let's say Bob wants to learn f of xy. Okay? There are more general things you could say. Bob wants to learn f of xy, Alice should learn g of xy, and so forth. But in some sense, this is kind of good enough. So we'll just stick to this. Bob wants to learn f of xy. Okay? So here is a little protocol. Alice prepares the function table for, so f is a two-input function, right? If I fix one input, I'll get a function of one input, of the remaining one input, right? So for each possible value of y, I have value of f of xy. X is fixed. You could run through all values of y, and you will get a bunch of values for f of xy. You could put them in a big list. That's a function table for this function fx with x hardwired in it, right? And takes y as an input. How big is this list? Well, it depends. It's the size of the domain for Bob, right? So if Bob's input is a y bit, Bob's input is y, the length of this input is this modulus of y, right, length of y. Then there are 2 to the y such bit strings, right? So that's as the size of his domain. Okay, y could be small, or say y is 5 bits, and that d is 32. Okay, so Alice prepares this list of 32 possible values of f of xy, depending on which y Bob has. And then Bob will just pick up one of these values using oblivious transfer. What I showed you in the previous slide was 1 out of 2 oblivious transfer. There are 2 pieces, and Bob was picking up one of them. But here what I want is 1 out of d oblivious transfer. So there are d pieces of information, d values, and Bob comes in and obliviously picks up one of them. All he learns is then f of xy, right? He doesn't learn anything else. And Alice learns nothing because there's oblivious transfer. She doesn't know which one you picked up. And Bob learns f of xy. From that, he could make some deductions about x, but nothing more, right? So of course, he'll learn f of xy. That's a functionality. And his view can be simulated just given the output from the ideal functionality. Okay? So that's why this is secure. So Bob learns only f of xy in addition to he already had y. And from that, he could make some deductions about x, but that's all allowed as legitimate information for him to get. Anything he can compute from f of xy. And Alice learns nothing beyond her input x. Okay, so in that sense, OT is the heart of 2PC, okay, or MPC more generally, multi-party computation. So what you just saw is a protocol, is a reduction from secure computation of any function to secure computation of OT. If this OT was replaced by a secure protocol for OT, the overall thing is a secure protocol for the function that for the function f. Okay, so say you can compute any function f if you have a secure protocol for OT. Of course, it came with a lot of caveats. Secure only against passive corruption, and further, it doesn't scale well. If Bob's input is 100 bits long, you cannot do this because there are 2 to the 100 possibilities, and Alice cannot create this big list. Also, I didn't tell you how to do 1 out of D OT, but that's not a problem. You can have D instances of 1 out of 2 OT, and it's an easy exercise to see how, against passive corruption, how to do 1 out of D OT from D instance of 1 out of 2 OT. Okay? So that's not the problem. The problem is this, that this D is really large. Okay? And how can we hope to fix it? Well, in some sense, you cannot really fix it, because at the end of the day, they are computing a function, and some functions are just computationally intensive. Functions on 100-bit inputs, we know for a fact that there are functions which do not have a small, computation, efficient computation, just because there are so many functions and there are only so many things you can do in a limited time. Because it follows from a counting argument, actually originally due to Shannon. So we know that there are functions which are very hard. We just don't know which functions are hard, unfortunately. But so we cannot hope to compute every function efficiently. So we have to use something about the function. Well, the kind of functions we are interested in are functions which have efficient computation if you didn't care about security, right? To begin with, the function should be efficiently computable if you are hoping to efficiently and securely compute it. So we only are interested in functions which have some efficient computation, and we have to exploit that computational representation, that algorithm in our protocol. Just having this function table to represent the function doesn't scale well. Okay, so we'll use Boolean circuits. Okay, there are other representations also that get used. There are algebraic circuits. There are branching programs. There are a few computational models that are good for MPC. What I'm going to show you today is something that works with Boolean circuits and in the two-party setting. Okay? So what is a Boolean circuit? It's basically this acyclic graph, directed acyclic graph. Okay, and the inputs are fed at the bottom, the output comes at the top, and you have the kind of a topological order from bottom to top, and the nodes in this graph are gates. Okay, so without loss of generality, they're all binary gates. They take 2 inputs and produce 1 output, and the wires are they carry bits, right, 0 or 1 value, and there are also constants that you can plug in, and there are inputs. All these blue things here are meant to be inputs that you feed in, and the red is the output gate. Okay. So each wire comes out of a unique gate, but it could fan out and it could go into multiple gates, right? So take this wire, it comes out of this gate, but it goes into 2 other gates. Okay, that's fan out. And there is as I said, there's a topological order in which you can evaluate these wires. So you could evaluate all of these wires in any order you want, but once you're done with that, you can evaluate. So once you have, say, both of these wires evaluated, then only can you evaluate this wire. This is a kind of next set of wires you could evaluate, then the next set, and so forth. Right? So you can say the sequential order is the order in which you would evaluate the gates. Okay. When you evaluate a gate, you get its output wire value. You do that until you get the output. So this is a computational model. Hope all of you are comfortable with this circuits model. There's nothing more to it, right? This all that is to it. And we'll assume that we are given a function in the form of a circuit that computes that function. So not all functions have small circuits, but we don't care. We only care about circuits which have small circuits, and we need to be given that circuit. Okay, once you have that, how do you do this evaluation securely? So we would like to evaluate any arbitrary Boolean circuit, and the model is that the circuit takes a bunch of inputs. Some of those inputs will be with Alice, and some of them will be with Bob. Okay, and we would like to evaluate it securely, so that the output, let's say, goes only to Bob. So yeah, one-sided output. And we want it to be secure against passive corruption of either party. Because if both of them are corrupt, then all we don't need to give any guarantees. We give security guarantees only to honest parties who follow our protocol, but the guarantee holds even if the other party is corrupt, in this case passively corrupt. So an adversary is observing the other party's head. Okay, I'll start with a simple example. So I'm building up towards a particular construction. And the construction is called Yao's garbage circuit. So we saw Andy Yao, was one of the people I mentioned yesterday, one of the Turing Award winners from from theoretical cryptography. And this idea was actually one of the first general purpose secure computation protocols, and due to Yao. Okay, so to build up towards that, let me start with a kind of a toy example, and that's to evaluate this function R. Okay, it's a there are 2 bits, 1 bit with Alice, 1 bit with Bob, and Bob wants to learn the OR of the 2 bits. Now we already have a protocol, right? I showed you if you have OT, you can just use one out of 2 OT to securely compute this. But I'm going to give you a more complicated protocol so that it can build towards the bigger final protocol. So Alice holds X, Bob holds Y, and they should get OR of XY.